Welcome to the Explainer. Today, we're going to pull back the curtain on Apache Kafka. We're going to follow a single message on its incredible journey, from the exact moment it's created, all the way to its final destination.
So here's how we'll break it down. First, we'll get that 30,000-foot view of a message's life cycle. Then we're going to zoom right in on how producers send data. After that, we'll uncover how brokers store it so incredibly fast. Next up is how consumers scale up to read it all. And finally, we'll talk about the delivery guarantees that make Kafka so reliable.
To really get Kafka, you have to visualize the entire journey. So let's map out exactly what happens to a single message from start to finish.
This right here is the fundamental flow. It all starts with a producer sending a record. The lead broker grabs it and writes it down, and at the same time, its followers make copies for safety. Then the leader gives the thumbs up back to the producer. That's the acknowledgement. Later, a consumer asks for new data, the broker sends it over, the consumer does its thing with the message, and finally, it bookmarks its spot. We're going to dig into the most important parts of this process.
All right, let's head to our first stop, the producer. This is where we, as developers, get to make some really critical choices that, honestly, affect the reliability of our entire system.
The very first decision is made by this little component called the partitioner. Just think of it like a mail sorter for your data. If your message has a key, like a user ID, the partitioner makes sure all messages for that user end up in the exact same partition. That's how you guarantee ordering. But if there's no key, it just deals them out one by one, round-robin style, to keep the load nice and balanced.
So this brings us to the crucial question for any developer using Kafka. How do you set up your acknowledgements, or ACKs? This one setting is the classic trade-off between going fast and being safe.
So, option 1. You can go for pure speed with ACKs equals 0. This is the fire and forget mode. It's like dropping a postcard in the mail. You just send it and hope for the best. It's blazing fast, but hey, if the broker blips out for even a second when you send it, that message is just gone. Great for something like metrics, probably a terrible idea for financial transactions.
Now, a much more balanced approach is ACKs equals 1. Here, the producer waits for just one confirmation from the leader of the partition. This gives you pretty good durability without a huge latency hit. The only risk? It's a rare one, but what if the leader says, "Got it," and then immediately crashes before its followers had a chance to copy the message? Yeah, you could lose data.
But for data you absolutely cannot lose, you use ACKs equals all. This is the certified letter that needs a signature from everyone. The leader broker will not send that confirmation back until every single one of its in-sync replicas also has a copy. Sure, it's a bit slower, but it's the safest you can possibly be.
But what happens if you use the safest setting, ACKs equals all? The message gets there perfectly, but the confirmation, the OK signal coming back to you, gets lost in the network. This creates a whole new, really frustrating problem: duplicate messages.
Here's how that disaster unfolds. 1. The producer sends the message. 2. The broker writes it perfectly and the replicas copy it. 3. The leader sends back the confirmation. 4. Poof, that confirmation vanishes in a network hiccup. Now, from your producer's point of view, the whole thing failed. So what does it do? It retries. And the broker, who has no idea this is a repeat, just says, "Oh, a new message," and writes it again. Boom, you now have a duplicate.
The solution to this mess is a powerful concept called being idempotent. An idempotent operation is something you can do over and over, and the result is the same as if you just did it once. Think about it. Setting your thermostat to 72 degrees is idempotent. Telling it to increase by 1 degree is not. We want our message sends to be like setting the thermostat.
And the way Kafka solves this is just brilliant. When you enable idempotence, the broker gives your producer its own unique ID. Then, your producer starts tagging every single message with a sequence number, 1, 2, 3, and so on. The broker keeps track of the last number it saw from your producer. So if a message comes in with a number it's already processed, it just says, "Ah, I see what's happening here. This is a retry," and simply throws it away. Problem solved.
Okay, we've talked a lot about safety. Now let's talk about what makes Kafka just ridiculously fast. Let's pop the hood on the broker and see why its simple storage design is actually its secret weapon.
You might be imagining some super complex proprietary database format, but nope, it's just files on a disk. Each partition is literally a directory, and inside are these append-only log files. New messages just get tacked onto the end. That's pretty much it.
But that log isn't one gigantic, unmanageable file.
It's broken into smaller chunks called segments. When a segment hits its size limit, it's closed, and a new one starts. Now, this is a genius move for data cleanup. If you set your data to expire after 7 days, Kafka doesn't have to hunt down and delete old records. It just deletes the entire old segment file. It's incredibly efficient.
So why is this simple approach so fast? Well, there are 3 big reasons. First, Kafka only writes sequentially to the end of a file, which is something spinning hard drives are amazing at. Second, it leans heavily on the operating system's page cache, meaning your most recent active data is probably being served straight out of RAM, not from a slow disk. And third, this is the secret sauce, it uses a technique called zero copy. This lets the OS send data directly from its memory cache to the network card, completely bypassing the Kafka application itself. It avoids so much wasteful data copying, and it's a huge part of why Kafka can rival in-memory systems. Okay, so we know how data gets in and how it's stored. Now for the other side of the coin, how do consumers read all this data, and how does Kafka give us massive, parallel processing power?
Scalability all comes down to consumer groups. You can throw a bunch of consumers into a group, and Kafka makes sure each partition is only read by one of them. Perfect. But anytime a consumer joins or leaves, maybe it crashed or you're scaling up, the group has to rebalance. It's like a stop-the-world event where everyone pauses to redistribute the workload.
Now, how that work gets shuffled around is super important. The default way, called round robin, can be a real pain. It often shuffles every single partition around, which is awful if your consumers have any kind of local cache or state. But there's a much smarter option, the sticky assigner. When a consumer leaves, it tries its best to only move the partitions that consumer was working on, leaving everyone else's work untouched. It is so much more efficient. All right, for our final section, let's tie everything together. We'll combine what we know about producers and consumers to really understand the specific delivery guarantees Kafka can give us. This table really sums it all up. You've got 3 main flavors. You can aim for at most once delivery by setting AX equals 0. That's your speed over safety choice. You can get at least once delivery by using AX equals 1 or all, but without the idempotent producer, you might get duplicates. Or you can have the gold standard, exactly once semantics. That's when you combine AX equals all with the idempotent producer. No data loss and no duplicates. And that quote really nails it. Getting the behavior you want from Kafka isn't about flipping one magic switch. It's about understanding this carefully orchestrated dance between all the different parts and configuring them to work in harmony.
And that brings us to the final and most important question. It's a question for you. Whether you're just logging some simple metrics, processing critical financial payments, or streaming live video, what's the right balance of performance, durability, and safety for your specific use case? The answer lies in the choices we've just explored.